Today we're going to be talking about section 1.3, vector equations. What is a vector? A vector is just an ordered list of numbers, and in fact we've seen them already. Last week we were looking at our systems of linear equations and trying to get them into reduced row echelon form. And we would have what we called a solution. And really our single solution that we're talking about was a set of two numbers, one for x1 and one for x2. So instead of calling this a solution, we could think of this as a solution vector. So the key part of this definition is that the entries in our vector are ordered. So for instance, if we have the vector 3, 5, this is not going to be equal to the vector 5, 3. If we think about this geometrically, then we can think about this as points in a plane. So Rn is the set of all column vectors with n entries. In this case, we're looking at R2, which is a name for the plane you might have seen before. So this is R2. And every single column vector with two entries in it would live in R2. We call these column vectors because they show up as columns in a matrix. So for instance, if we plotted out 3, 5, that would be over here. And if we plotted out 5, 3, that would be over here. These are clearly not the same. So two vectors in Rn are equal if their corresponding entries are equal. So not only do the numbers in the vector have to be the same, they have to be in the same order. What can we do with vectors? Well, we can add them. So for instance, if we had the vector -2, 3, and we wanted to add to it the vector 4, 1, we can add these pretty easily exactly as you'd really want to, which is just adding across each corresponding entry. So our first entry in our sum would be the sum of the first entries in our vectors that we're adding together. So we'd have -2 plus 4 is 2, and 3 plus 1 is 4, and there's our sum. You might have seen this geometrically in other classes before. Sometimes we represent vectors as an arrow pointing to that point from the origin. So -2, 3 would be, let's say, around here. There's our vector -2, 3. 4, 1 would maybe be around here. And what we're doing when we're adding geometrically is our sum is the other point of that parallelogram. So if we went ahead and filled out this parallelogram, here's our 2, 4, and well, not to scale, but this kind of looks like it could be 2, 4. All right. The other thing we can do in addition to adding the vectors is we can scale by a constant. So for instance, we could take 3 times 1, 2, and again, this works the way that you'd hope it would, where we get the product here just by multiplying each entry in our vector by our scalar multiple. So our first entry would be 3 times 1, which is 3. Our second entry would be 3 times 2, which is 6. Geometrically, what this looks like is we have our original vector 1, 2, which is maybe here. What we're doing when we multiply by 3 is we're just stretching this out by a factor of 3. So maybe we're up here. So we're just stretching that vector out. There are some properties of vectors that we should talk about. All of them are exactly what you would hope would be true. So hopefully none of these will come as a surprise. Basically, here they are. If you have two vectors, it does not matter what order you add them in because all you're doing is adding component-wise and adding real numbers. The order doesn't matter. It's associative, so you could add the first two vectors first and then add the third one, or first add the second two and then add the first one. If you add the 0 vector to any vector, you're just adding the 0 to every single component, so you get the same thing back again. If you subtract a vector from itself, you'll get the vector of all zeros. This c is a constant, so I won't put a little arrow over it. The c is a real number, like our 3 in the last example. So if you take the sum of two vectors and then multiply it by a constant, we have the distributive property here. You could instead first multiply each vector by that constant and then add them together. Similarly, if we have two constants and add them together and then multiply them by the vector, we could first multiply each one by the vector and add them. And if we multiply a constant by a vector and then multiply that by another constant, we could first multiply the two constants together. And lastly, if we multiply a vector by the constant 1, what are we doing? We're multiplying every corresponding entry by 1, which will just give us the same thing. So here are our properties. If you're having trouble grabbing onto any of these, you can go ahead and try them out on an example, and they should become pretty clear. All right, so how do vectors relate to what we've been talking about? Well, we can combine vectors, as we just saw, using scalar multiplication and addition. And if we do that, that's something called a linear combination. So let's take a look at this. A vector y is going to be a linear combination of a set of vectors. So y is a linear combination of v1, v2, vp. These are supposed to be subscripts, but apparently Ring Central doesn't do that. So y is a linear combination of a set of vectors if there exists weights c1 through cp, so these are just real numbers, such that we can write y as c1 times v1, so this is a scalar multiple of v1, and then we can add to that c2, v2, and so on. So this is what it means for a vector to be a linear combination. So for instance, if we take this, the vector that we get by scaling, let's say 3, 5, 1 by 2, and adding to that 7 times minus 2, 4, 3. If we do this out, this would be a linear combination of the vectors 3, 5, 1, and minus 2, 4, 3. So we could easily do that and find ourselves a linear combination of those two vectors. Yeah. A much more interesting question is, if I'm given a vector, is it a linear combination of something? So let's take a look at what that might look like. So here's our example. Our question is the vector 2, -1, 6 a linear combination of, let's say these three vectors, 1, -2, 0, 0, 1, 2, and 5, -6, 8. Well, how might we figure it out? What would it mean for 2, -1, 6 to be a linear combination of these things? What it would mean is here, the 2, -1, 6 would be our y. So we've got 2, -1, 6. And our question is, do there exist numbers C1, C2, and C3 where we can satisfy this equation, right? So I'm literally just pulling this from the definition that we have right above there. So can we find these C1, C2, and C3 so this equation is satisfied? Okay, well, what would it mean for the C1, C2, and C3 to exist? Well, all three of these entries in the vector would have to work. So we'd have to have 2 equals C1 times 1 plus C2 times 0 plus C3 times 5. So this is the first entry in each of these vectors. And then simultaneously, we'd need to have the second entry work as well. So we'd need -1 to equal C1 times -2, C1 times -2 plus C2 times 1 plus C3 times -6. And at the same time, we'd also need 6 to equal C1 times 0 plus C2 times 2 plus C3 times 8. Well, interestingly, this looks like what we've been doing all last week, which is looking at a system of linear equations. So we can think of this as a system of linear equations where C1, C2, and C3 are our variables. So we can put this into an augmented matrix where our matrix would look like 1, 0, 5, that should equal 2, -2, 1, -6, that should equal -1, and 0 to 8, and that should equal to 6. So really, when we're asking, is this vector a linear combination of these other vectors, we're asking, does the system of linear equations have a solution? Is it consistent? And we know exactly how to do that. We try to get it down into reduced row echelon form and see what our answer is. I won't do that in this video, but presumably you can do that because we've been doing it all last week. If you want to try it out on your own for practice, go ahead. So this brings us to sort of the main realization of why we look at linear combinations, which is that if we want to know if a vector is a linear combination, B is going to be a linear combination of, let's say, the vectors A1 through AN. This will have a solution. This will have a solution if and only if the augmented matrix where each of the columns is each of our vectors in our linear combination, and then we augment it with the thing we want to know about. So here's our B, is this a linear combination? So this has a solution if and only if this augmented matrix is consistent. So really, our question about linear combinations is just a question about reduced row echelon form and consistent linear equations in disguise. The last thing I want to mention is that if we look at the set of all linear combinations, this has a special name. So the set of all linear combinations of a set of vectors is called the span. So the set of all linear combinations is the subset of Rn that's spanned by those vectors. So this is another way of writing this is the span of the set V1, V2 through Vn. So our previous example was saying, is this specific vector a linear combination? If we look at all the vectors that are linear combinations of those vectors, that's called the span. So another question, instead of saying, is this a linear combination of these vectors, we could say, is this vector in the span of these vectors? Great, that's all I have for you today. And I'll see you in class.